Okay, so we'll give a title to this in a second, but here we go. Let's say I had a metal sphere, actually two metal spheres, and the first one was charged negatively, let's say negative 12e, meaning it has 12 excess electrons, and let's say this one is charged positively, let's say positive 10e, so it is lacking 10 electrons. So in the region surrounding these two charges would be an electric field, right? And that electric field would go from the positive to the negative in that beautiful pattern that we talked about. I'm not going to draw it because that's not what we're talking about here today. So what that would mean would be any charge, free charge, if I placed it in this location, would follow those electric field lines if placed at rest to go from one charge to the other, depending on whether that free charge was positive or that free charge was negative. Now, that's one thing. But now let's imagine, rather than having free charges in this free space, I instead take a conductor, like a copper wire, and I connect the two. Well, what would happen in that case? Well, let's remember something. If there was an electric field in this region, the electric field, once again, is the same thing as the potential gradient. So if the electric field is not equal to 0, that must mean in any region where there is an electric field, there must be a potential difference between those 2 points in space. Meaning, there's a potential difference between this positive charged object and this negative charged object. So there exists a delta V here, a potential difference. Okay. Now, what would happen in this particular situation? Well, hopefully what you would say is, I have a high electron concentration here and a low electron concentration here. So what's going to happen is some of these excess electrons are going to want to flow over in this direction to the positive. Now, hold on a second. I just have to move my table because it's shaking. I want to put it up against the wall to stop it shaking. There we go. Right? So there would be an electron flow from the negative sphere over to the positive sphere. Well, why is that? Well, once again, we said that wherever there is a potential difference, that charges are going to want to flow to a place where they have lower electrical potential energy. In this case, that would be excess electrons going from here to here, because these excess electrons are all pushing on each other, and here there's a lack of electrons, so they're going to pull over some of those excess electrons. And so I have that flow of charge. I'm going to give a name to that flow of charge. A flow of charge is called a current, right? A flow of charge. Now, this very specifically is something that's called an electron current because it's a flow of electrons. And that's actually what's happening when we talk about the notion of current is a flow of electrons. Now, we'll get back to that flow in a little bit. So what's eventually going to happen here? Well, eventually, this system would get to a place such that the flow would stop. Well, what would be true when it stopped flowing? Well, charge would flow until there's an equal concentration of charges on all these objects. Now, these two metal spheres were of the same size, so what's going to happen here is charges are going to flow until each of them has the same charge, right? Now, that's not always true, but because these two objects, let's say they're identical objects, that would mean that would be the minimum concentration on each. And now we would say here, the potential difference between these two plates would be some number, but the potential difference between these plates with balls here, the potential difference here would be 0. And so what I want to associate then with the concept of current is that if there is free charge and a potential difference between two locations in space, and a conductive pathway, right? Because remember, there was no charge flowing when it was just like air here. Right? Charge will flow from, one way to say this is high electron concentration. Oh God, I just wrote contraction or contration. Concentration to low electron concentration. Until there is an equilibrium. And that would be equal concentrations of electrons. Okay, but I'm going to phrase that differently now. Rather than talk about electron concentration, we can now talk in terms of potential. Because here there was a potential difference, here there's no potential difference, and there's no flow. So charge is going to flow where there's a potential difference until the potential difference has gone away, right? Once again, so another way of talking about equilibrium would be equal potentials. All right, let's look at another situation with that same idea, right? Let's say I had the two metal spheres and they're equally sized. So plus 10e and then plus 16e. What would happen if I can connect them? Well, once again, we would have a flow of electrons. But which of these has a greater concentration of electrons? It's actually this one here that's missing 10 electrons. This one's missing 16 electrons. So charge would flow in this direction. Electrons would flow until the concentration of electrons is equal. In that case, it would be plus 13e. Right? Now, these are really minuscule, small charges, just easier to think in terms of these numbers. Right? And then the charge flow would stop. So how many electrons flowed over? Right? Hopefully you figured out it's 3. Okay? So it's not necessarily just, from the bigger number to the smaller number. It's higher electron concentration to lower electron concentration. So you have to be conscious about that. But I'm not really too concerned with this particular thing, although I'll do just one more sort of interesting thing. Let's say you have a big object and a small object here. And let's say this has, negative 20e, and this is initially neutral, and they were to be connected. Yes, electrons would flow, but what do you think would be true about the end state here? Well, hopefully what you said is they wouldn't have equal amounts of charge because all they're required to do is have equal concentrations of charge, i.e. equal potentials. But because this object is so much larger, what you may see something like is that this might be negative 16e and this would be negative 4e in order to get that equal concentration, and then the charge flow would stop. If we want to actually know what's going on here, well, concentration would be charge Q, actually, I'll do capital Q here, per surface area. And that's what would have to be equal on both, right? So in other words, Q per 4 pi r squared, because that's the surface area of the sphere here. And so that would have to be the same on these two things. And that r squared thing is why this is not an equal distribution like that. But what we're really concerned with today is this idea of the flow of charge, not so much about this, right? So let's talk about that flow of charge, or that current. So first off, current, there's a symbol for current, I, capital I, by the way, not lowercase I. You know lowercase I as, of course, the imaginary number, right? So we don't want to be using that for too many things here. So let's talk about this now. Yes, this is the flow of charge, but how would I measure a current? Or really what it is, well, what do I need for current to form before we talk about quantifying that notion of current, right? So when you're thinking about the notion of current, what are you normally used to thinking about? Well, hopefully what you're used to thinking about are water currents, right? So when do you get a current of water? Well, hopefully what you realize is that you get a current of water often. If you think about a river, rivers always flow from high places down to low places, right? Going from higher elevations down to lower elevations. Well, why is that? Well, even water current, there needs to be a difference in potential between the two locations in space, right? So like if this is my hill, we know that water is going to flow down the hill like this, right? If this was a flat, the water wouldn't go anywhere. We'd have a puddle or a pond, right? So the first thing that we need in order to have a current is to have a difference in potential between two locations. That's super easy when we're talking about gravity, a difference in gravitational potential. It's just one has to be elevated over the other. If we're talking about charge, that means I need to have charge imbalances. I need to have something that is positive and something that's negative, or that there's something that's really, really positive and something that's not as positive, or really, really negative and something that's not as negative. There just needs to be a distinction in charge balance, or a concentration, electron concentration between 2 points in space. So remember, that also means that there must be an electric field. Because wherever we have a difference in potential between 2 points in space, there's always an electric field between those same 2 points, pointing from the higher potential, meaning the more positive thing, to the lower potential, the more negative thing. All right. Now, the second thing, if I just have a hill, like for example, let's take, I made some toast. So here I have a hill, ignore the crumbs, but there's nothing flowing. There's no flow of anything. Why? Well, there's nothing to flow. Yeah, fine, there's some crumbs, but let's just ignore that, right? So if I want a water current, obviously I need water, right? But if I want a current in terms of what we're used to talking about in current, what I need is a source of free charge. Now, back in these examples, these materials, because they were conductors, had loosely bound electrons, and therefore those electrons would redistribute around those conductors in order for the system to reach equilibrium. Next, what I would need is a conductive pathway, right? If there's no way for the charge to get from one location to the next, you don't get anything. So there you go. Now, we had all of that going on in this scenario. We had a difference in potential, a conductive pathway, and our source of charge was just the excess charge here on this particular object. And it flowed until we reached there to be an equal potential and therefore no flow. Same thing here. If we had water on a surface and we tilted one end up, right? Like if I had water on my plate and I tilted the plate up, the water would rush down to the lower potential or the lower elevation, and then I'd be done. But that wouldn't be very interesting, right? Because after a while, the flow stops when all of the water or the free charge gets to the point of lowest potential energy. Notice I didn't say lowest potential there. I said lowest potential energy, right? And so what I would need then, if I wanted a continual flow of charge, I need something that maintains this potential difference, right? For example, here the potential difference went away because when the charge distributions evened out, the potential difference went away, right? So if I want a continuous current, I need to maintain the potential difference. Well, let's use our gravity example here. Well, what would I need in this case? Well, what I would need is something that took water from down here and brought it back up here. Yes? Like a pump, right? And so that pump would do work on the water to give it gravitational potential energy, and then down it would go. Then do work, down it would go. It wouldn't be very useful, right? Maybe there's you know, a nice water feature here, so it's pretty and all, but it's not very useful. But it would be a continuous flow of current. Well, what would I need here in order to have a continuous flow of current? Well, our charge would flow over to this place, and what I would need is something when the electrons got over here to take the electrons and do work on them to bring them back over here. Okay, such that then they would want to keep going down here. So I would be maintaining that potential difference because I need something to do the work to give them electrical potential energy in. So I need to maintain the potential difference. Another way to say that is I need something to do work on the charge to bring to higher electrical potential energy. And so that's what we've got going on there. So let's talk about that. Notice then, let's not notice, let's actually look at an example. I have a light bulb, right? My light bulb is not doing anything. Well, what do I know can maintain a potential difference? Well, potential difference is measured in volts, joules per coulomb. Well, what do I know has joules per coulomb on it? Well, hopefully what you have thought of is a battery. Now, this is a 6-volt hobby battery, right? 6 volts, 6 joules per coulomb. And then this is the positive terminal of the battery, and this is the negative terminal of the battery, right? And this thing is functionally like a pump for electrons, right? So this, what's called terminal of the battery, maintains a negative concentration, and this one is a positive. So this has lacking electrons, and this has an excess electrons. What you may hopefully remember from chemistry is there is a reaction going on inside of this called a redox reaction, that one of the things inside of here is being oxidized and one of them is being reduced. Therefore, one of them is going to maintain a negative charge and the other a positive charge, maintaining that potential difference. So as long as that reaction is going on inside here. Now, the reaction right now is not going on, but we can make it go on. Well, how do we make it go on? Well, right now, let's see what I have. I have a difference in potential between two locations, here and here. But what I don't seem to have here is a source of free charge and a conductive pathway. So here's the first thing we're going to say. The battery is not a source of free charge. A battery is not like a little well of charge. The battery is just something that does work on charges that brings them from here through the salt bridge, etc., that you should remember from your electrochemistry unit last year, to the negative, and does work on them as that happens. So what do I need then to do a conductive pathway and our source of free charge? Well, what I've got here are wires, right? That's my conductive pathway. So here you go. I'm going to attach a wire to the negative terminal, and then I will go to, let's say, one side of my light bulb. And then I'm going to take a second one. I'm going to attach that here. And notice right now, I have a conductive pathway, I have a difference in potential, but nothing is happening. Well, nothing is happening because if you look back at what we were talking about over here, every time I drew the pump, what it did was it created a closed system, right? So it's not like these electrons were coming from somewhere randomly. They were coming from here and being brought there. So what I need to do is close the pathway. So here's the other end of that. If I attach it to the positive end of the battery, voila, I've got that. That's my evidence that there is a current flowing. So what I have here is something that's called an electrical circuit, but very specifically a closed electrical circuit. The electrical circuit is just defined as, or rather a circuit is just defined as that pathway. But in order to get a current to flow, I need a closed pathway. Watch what happens when I unscrew the light bulb. The light bulb goes out. There's no current now because there's no closed pathway. Screw it back in. There we go. A little bit more fun application, then we're going to go back into that. I have this happy thing here. Looks like a ping pong ball, but if you notice, it's got these two little electrodes on it. I'm just going to steal another wire here, and I want to show you something that happens. Notice here, connect that there. And then if I take another, that's really hard to hold it in place. If I take another wire, whoops, or at the other end of the wire, whoops, I just dropped that on the ground, right? When I close the pathway, so what must be inside the ping pong ball? What must be inside the ping? It must be inside the ping pong ball, and I'm not going to break it open. Must be a battery of some description, as well as something that's doing that noise making. Now, even more fun than that. Watch this. Boom. When I landed, it broke the light. Oh, there it goes. Right? So, hold on. Well, what does that say? Well, what that says is that our body is a conductive pathway, right? Our nervous system is a conductive pathway, and actually there is a very low current electricity flowing through my body right now in order to do that. I don't even have to do the two hands. There we go. Boom. And this would be fun because if you're in class, I could put one finger here and hold hands with someone on one side of the room. We could link our hands all the way around, and the last person could touch that, and there you would go. Boom. That's what would happen. It would have been fun. Oh well. All right, so the title for all of this that we're talking about here is circuits, right? A circuit. A circuit is just a pathway around which current can flow. And if my circuit is closed, notice I say can flow, right? If a closed circuit with a source of potential difference, therefore you get a current. If I have an open circuit, there is no current that flows. So here's what we have. Just to draw a little picture, I've got my 6-volt battery. This one was the positive terminal, that one's the negative. Here's my 6-volt battery. And then I attach this to one end of a light bulb. I'll just do that as my light bulb. And attach the other end to this part of the light bulb. And there we go, the light bulb went off and started glowing. So what's going on there, right? Well, I have a source of potential difference because of the chemical reaction that's going on here. So chemical energy is becoming electrical potential energy. And so what's happening here is there's a potential difference in the wire. And if there's a potential difference in the wire, okay, so potential difference in the wire, what that means is that there's an electric field in the wire. Because that battery here is a source of potential difference. Another way of saying that is it's a source of energy, right? Because what that battery is doing is it's doing work to bring electrons from the positive to the negative terminal. And so what that's happening then is the electrons then, because they're being brought from here to here, now I have a concentration of electrons and the electrons start flowing through. But where do the electrons come from in the first place? Well, the hint is here. There's an electric field in the wire. Well, what's a wire made out of? Well, it's a conductive pathway, and a conductor has lots of free electrons. So literally, when I close the loop, that creates an electric field all throughout this wire, and free electrons in the wire start flowing from the region of high electron concentration to low electron concentration, then they're brought back up to the high concentration, and on they go. So the source of the free electrons here is the conductive pathway. All right. Now, there you go, some very practical things. So the battery is not the source of the charge, it's the reason why the charge begins moving, okay? So, what else is happening here? Well, I already talked about there being chemical energy here that was doing work to bring the charges from here to here, giving them electrical potential energy. So we have a transformation of chemical energy to electrical energy. Then electrical energy, well, what's happening here? Well, notice here my light bulb. What transformation is happening there? Well, that electrical energy is becoming light and heat energy here. And that's actually what the point of a circuit is, folks, right? Because remember when I showed you just our this thing here, this is rather useless. Water flows down, gets pumped back up, flows down. It's like, it's just endless and meaningless. But it's not meaningless if I, for example, put a water wheel here, such that as the water flows, it turns the water wheel. This is connected to an axle, which I don't know, like turns a motor or turns a generator or something, right? This now becomes useful because it's in the pathway of the flow. So in a lot of ways, as the water gets through here, some of this potential energy gets transferred to this object that's doing useful something with it. Well, that's what's happening at the light bulb here. It's in the way of the flow, and the energy that the charges have is being transferred to this object here in order for it to do something useful. We're going to give a name to this idea, it's a light bulb here, but like for example in this, it wasn't just a light bulb, it was also a sound making thing, right? But what happens if that thing is a motor or your toaster or your TV or whatever? I'm just going to give a general name to this object here, and I'm going to call it what seems to not be a good term, and we'll talk about this in the next video, something we're going to call a resistor. A resistor is poorly named, but it is anything that can transform electrical energy into some other useful form, or not even useful, just some other form, right? Because actually, if you just take a wire and you connect it to both ends of a battery, I don't recommend that you do this, because if you're holding that wire, it's going to get really hot really quickly. That's not useful, but that is a transformation of energy. That's because wires, even though they're a conductive pathway, also are resistors. All right, so anything that can transform electrical energy to some other form. So what's the point here? Well, what's the point of a circuit? The point of a circuit then is it is a mechanism of energy transfer using charge as the method or the agent of transfer. Okay, that's the point. So here, I'm taking my charges, forcing them to move, and what those charges are doing is they are carrying energy from here, they're delivering it here, and then those charges are going back to here. Work gets done on them from the chemical energy in here, giving them more energy, and then they transfer the energy here, and they go back and they keep going and going and going until this battery can no longer do work. That's why batteries run out. It's because what's happening here is every time a charge is brought, a single chemical reaction happens that does that, one redox reaction. Based on the number of chemicals in here, that it can only do so many redox reactions. That's why larger batteries last longer, not because they have more charge and they're giving it out. It's because they have more chemicals that can individually do more of those chemical reactions to give each charge the same amount of energy. Because what this is saying is that each coulomb of charge that gets through gets 6 joules of energy. Or if we want to bring this down to the atomic level, work equals Q delta V. If I have one electron, that's negative 1e, but like we're not using signs here, times 6. Each electron gets 6 EVs of energy, and it's delivering that to here. So the way we want to think about a circuit is the circuit is like the post office. What? Yeah, it's like the post office. The battery is like the post office. We know that male people walk circuits, come back to the post office. Every male person that leaves comes back, right? And they walk that same loop over and over and over again. And what are they delivering? Mail. Well, what our electrons delivering here is energy. But here, when, for example, a male person goes to the resistor, which in this case would be the house, it just drops off mail. Does the house consume the male person? No, it does not, unless Jeffrey Dahmer lives in that house. But let's not talk about that, right? The electrons in the same way deliver energy, but then continue on, and then deliver more energy, and then continue on. So really, electrons are just the mechanism of energy transfer from the potential difference source to what's going on over here. Now, we'll talk a little bit more specifically about what's happening here in a quantitative way in the next video, but that's the logic of a circuit, is that charge is being forced to flow through a path and bring energy from one location to another. And so then we will look at the concept of resistors, current, potential difference, and how to quantify all these things in the next video.